Hello, this is Teresa Stack, Associate Professor from Montana Tech, and the following learning unit is a review for the sampling for evaluation of health hazards midterm review. So I'm giving you an example of questions which you may see on the exam. So you plan to sample 8 workers for ammonia, which is a gas. Based on the work process, you have determined that 4 samples per worker will be sufficient. Based on the sampling method below, what is the desired flow rate and time for each sample to be within the method? Show your work for full credit. So we're interested in this area of the method, and we can set it up a number of ways. So the first way we can set it up is by using the equation Q, which is flow, equals volume divided by time. And we have a variable flow rate here between 0.1 and 0.2 liters per minute. But we know that we want to sample 4 workers for an 8-hour shift. So that means we're going to run for a time of 120 minutes. This is our target time. And our minimum sample volume is really low. It's 0.1 liter. So you can see if we chose a flow rate of 1 liter per minute and we ran for a minute, we'd be able to meet our minimum flow rate. So we're probably most concerned with the maximum flow rate there, since it seems to be more sensitive to time. So let's take our formula. Our maximum volume is 96 liters. And our time is 120 minutes. So if we divide 96 divided by 120, this will give us 0.8 liters per minute. Is 0.8 liters per minute within our method? No, it's not. It's actually much too high. So we need to choose a lower flow rate. Let's look at the highest flow rate acceptable. So our maximum flow rate, according to the method, is 0.2 liters per minute. And we still want to sample for 120 minutes. And now we need to figure out how much air we'll pull, and that's what our sample volume is. So we have 120 times 0.2 24 liters. And therefore, if we set our sampling pump to 0.2 liters per minute, which is within our method, and we sample for 120 minutes, which gives us 4 samples per worker, we would draw 24 liters of air, which is well within our method. Okay, so question 2. You plan to sample 8 workers for ammonia using the method above, 4 samples per worker. How many pieces of media do you need? Of course, we need to show our work. So we could start with 8 workers times 4 media equals 32 media for samples plus 1 calibration media plus, let's see, how many blanks? 2 to 10 field blanks. So we could say 2 field blanks, and this would give us 35 media. Another way to solve this would be 10% of your samples for the blanks. And since we had 32, that would equal 3 field blanks, or 36 pieces of media. You, of course, also can add 1 or 2 extra pieces of media as a backup in case something happened during your campaign. But at a minimum, you would need between 35 and 36 pieces of media. Okay, on to question 3. You sampled for metalworking fluids, and the method is below. Please make sure you recognize that there are 2 different ways you can sample for metalworking fluids, either respirable or thoracic, and this is the or respirable or total, and we're looking at the total particulate matter. And you sample 2 workers 2 times. The data is below. Which flow rate do you use to calculate the sample volume for each pump? So the question is, which flow rate do you use to calculate the sample volume? So we'll start here with our we know that first we have to solve for our percent error, which is pre-calibration minus post-calibration divided by pre-calibration. So my percent error was 3.9%, and therefore I can use the average. And now I'll take the average flow rate, which would be pre plus post divided by 2. And I must have done something wrong. $2.015 liters per minute. So here is the answer to part 1. Now the second question, using the flow rate found in part 1, calculate the total sample volume sent to the lab and indicate whether each is within the method. Well, so we're going to use, again, our same formula, Q equals V over T, and I have my flow rate now, and I'm going to multiply it by my time. So times 386 minutes would give me a V of 791.68. 791.68. And then I go back and take my average flow rate times time, 673.01. So now these are the answers to the second part of the question. calculate the total sample volume, and you would of course continue it for the ones that are down here, making sure that you note that there is a different pre and post calibration because you have two different pumps, and indicate whether it was within the method or not. So here our method tells us that we can sample for total metalworking fluids at 2 liters per minute, and we were close to 2 liters per minute, and that we have a minimum sample volume of 768 liters. So yes, in the method. No. And this gives us the answer to part 1 and part 2. So for the next problem, we're going to calculate a time-weighted average. So you can see we had 2 workers, and each worker had 3 samples. So we need to weight the concentration by the time. And so we'll start here at the top. So we know that a time-weighted average is the sum of concentration times time divided by the sum of time. So let's do concentration times time. 9.01 times 200 . 10.58 times 158 . And I am just using, I'm rounding here instead of using all the decimal points. I won't be able to remember the numbers back and forth, and I believe you can still understand the process. Now I'm going to sum time. So I have 200 plus 158 plus 149, 507. Okay, so now I'm going to sum my concentration times time and divide by the sum of time. So there's my sum of concentration times time, and now I'll divide by my sum of time. And my time-weighted average is 7.925. 7.925 milligrams per cubic meter. So our next step would be to calculate our upper and our lower confidence interval. And we know the formula for that is y equals plus or minus the standard analytical error, where y equals the time-weighted average or the concentration divided by the OEL. So here my y is going to equal the time-weighted average divided by the OEL. The OEL is up here. So my severity, or my y, is 0.79. So you can think this exposure is almost 80% of the occupational exposure limit. It's pretty far beneath, but let's still run the numbers anyways. So our upper confidence interval is 0.79 plus our standard analytical error. And our lower confidence interval is minus our standard analytical error. And we can see that because both the upper and the lower are less than 1, we are within compliance. So for question 4, you'll be adjusting the occupational exposure limit, or the PEL, for metal dust given the work week that you see above. And you would need to have these formulas, which I did not have them memorized. So I put them in for you. So for our daily value, 12 hours is the longest work day, and for the weekly value, let's see how many hours this person worked in a week. 11. And now we simply plug those values into the equations that you see below. To get full credit in class, you would need to write the equations. So I have 8 divided by 12 is 0.66. And the second part of the equation, 24 minus 12 divided by 16, 0.75. And when I multiply that by the first part of the equation, I get a reduction factor of 0.4995. And if I take that value and multiply it by the permissible exposure limit for metal dust, which I would have found in the previous problem, it means that I'm reducing the occupational exposure limit to 4.995 milligrams per cubic meter. And of course we need to round for significant digits here, but I'm just moving along and showing you how to do the math. And now we need to do it for our weekly value. Make sure we don't end there, or we may make a mistake. So let's take a look at that one, which would be 40 divided by 44 is 0.909 times the second part of the equation. .968. I multiply that by the first part of the equation, gives me a reduction factor of 0.88. And my adjusted PEL for the weekly factor, .8. Therefore, the adjusted PL is 4.99 milligrams per cubic meter because it's the smaller of the two. So we're taking the more conservative approach when we're doing our adjustments based on this 12-hour workday. Question 5. Workers are exposed to benzene, toluene, and styrene. They all target the same organs. Calculate the total value for additive effects. And so we would need to have the proper formula for that. It's the total value equals the concentration, or the time-weighted average, and we divide that by the OEL. And then we keep adding these together, and that's how we calculate the total value when we're using additive effects. We do not do this when we're doing mixture effects. And so you have this formula, and I will then do the calculation for you. So we just take the ratio of each one, which is our severity, and we add them together and see what the total value is, whether it exceeds 1 or not. And it's a way in which you're combining these different occupational exposure limits together. So the actual exposure was 205, and I divide that by 200, and it gives me 1.025, which means I'm already over, but let's do it anyways. The next one, the actual exposure was 0.078, and I divide that by the allowable. So I'm 78% of the occupational exposure limit on benzene. Now for styrene, 98 divided by 100. And if I add these together, if I take this and multiply it by 100, you could see I'm 278% of the combined OEL, and we have an overexposure because the total value is greater than 1. So that's about it for the review. Other topics that may be covered include adjusting a sample volume for changes in temperature and pressure, different types of calibration methodology when they would be used, types of calibrators, and potentially some questions concerning dose versus exposure, and the limit of detection versus the limit of quantification. Certainly the other review is important as well as this one. I hope you have a pleasant day.